All right, I think we'll get started. Today we have Frankie Cho back from, he used to be here at UQ, he did his PhD with Jonathan, and now he's doing a postdoc at QUT. And he's kind of the face of CBCS. If anyone's seen the video, the CBCS video, it's like totally featured in it.
I haven't seen it.
So that's why he became famous. And then we just run with him since then. So he's going to talk about prioritizer. Raise your hand if it is prioritizer. Yeah, few people. Okay, so few people know what it is. Raise your hand if you want to use it. If you're like looking to, you know. Cool. Okay, so all right, so we'll hand it over to Frankie for presentation.
Marissa, can people online hear me okay? Should I use this?
No,
Just stand here. Okay. Hi everyone. So welcome to this talk. Today I'm going to talk a little bit about some of the open source work that I've been doing with Jeff Hanson on robust systematic conservation planning. So I think some of you might have used the prioritizer package, and so this is essentially an extension that will allow us to do robust versions of our existing conservation planning problems. And just a little bit about myself, I am currently a postdoc research fellow at QUT. They have a new center called the Center for Environment and Society. So, and certainly a lot of amazing work going on in terms of biodiversity conservation, as well as and the integration between environment and society happening there as well. So I thought I'd just mention that. So let's begin. So before we begin, I'd like to acknowledge the traditional owners, custodians of the lands with where we meet today. We are meeting today, I think it is also on Turral and Yagara land. And these lands are First Nation owners, land that have never been ceded and always been places of teaching and learning. So I'm really proud to be sharing some knowledge and experiences about this topic today, and as well as and being able to take part in the learning teaching activities that have already taken place by the First Nations on this topic. So let's begin. So I think a lot of you know that there's a mountain of evidence that would suggest that species ranges are going to shift dramatically under climate change. I'm just reviewing a couple of examples here. A lot of you might have worked on other examples of how species are going to move, and a lot of times move outside of protected area fences. We have the first paper on the left that shows that it really shapes ecosystem and human well-being, and this is really important for our ecosystem services, as well as safeguarding the species from further decline and bending the overall trend in biodiversity loss. And there's also increasing evidence that shows in this paper that shows that these range shifts would cross political borders and would definitely cross the protected area fences of the protected areas that we put in today. And I think a lot of you might also know the recent paper by Max Kotz that shows that these impacts, the impacts that climate change have on species, are already occurring. Heat extreme intensification is already driving bird abundance declines, and he talked about a lot of his work a couple of months ago. And I just want to mention that these impacts are already underway. We are already seeing these impacts, and therefore it's imperative for us to be thinking about protected areas that are robust to some of these changes that we are going to observe in the coming decades. And just a brief introduction about what systematic conservation planning is. So I think a lot of you might know, systematic conservation planning is a transparent framework for us to select, prioritize, and prioritize different parcels for protection. In this case, selecting the blue parcel over here by integrating a couple of data layers. So one, we want to integrate the features of that will represent where the species lie in space. So here we have one feature, but we could have several different features of different species that we want to protect. And there's also a cost layer usually that tells us how much it is for how much will it cost the decision maker or society to protect each particular parcel. As we can imagine, some of these parcels are more expensive because there are higher opportunity costs from protection. For example, there could be more alternative uses of land, and therefore be more expensive, and it also can also be more expensive for some of these conservation agencies to acquire land in certain areas. We want to integrate these into a common framework. For example, and be very explicit about our objectives and our constraints here. For example, and this is just one way we can formulate this problem, we minimize total costs subject to the fact that we meet all of our targets for representation. So let's say we want to represent one cell, at least one cell in the features that that covers the green areas over there. That's where the species are located, subject to or like with the overall objective of minimizing total cost. So this is what we would mean by systematic conservation planning or prioritization, and a lot of these prioritization tools help you achieve something like this. And the problem is quite going to be apparent under climate change. So on the left-hand side of both on the two panels, we see the current climate. So the green areas would show where a hypothetical bird species would lie in space, and the blue square would show where we would put our protection. And as we know that some of these protection, the amount of protection that we put can be severely limited by the amount of budget that the conservation agency has, as well as also other constraints that prevent us from putting protected areas in certain places. So if we only put this blue square over here, and then we are confronted with a future climate here, and the birds, as I've mentioned, will move across space, given climate change effects we're in the southern hemisphere, so to track climatic niches, the bird will move further to the south, because now this cell on the bottom has the same climate as what used to be on the top left. So that means that the bird species that we're trying to protect, and we do our conservation prioritization, will go outside of our protected area fence, and therefore our protected areas will be not so effective. What we want to do is what we want to see on the right-hand side, where we have, regardless of the future climate, regardless of whether the species lie on the what looks like on the left or on the right, we want to ensure that at least one bird is protected, such that this bird is continually represented in our protected area network. In this case, even by selecting also the square on the bottom right, we ensure that the bird is continually protected in the current climate, as well as in the future climate, as well as in several plausible future climates that we have in our data set. So what do we mean by protecting that across not just one future climate, but several different future climates? Here is what we as an analyst would typically face. On the left-hand side, we see the conventional approach to selecting or prioritizing a conservation area, and we have several different data realizations. So what are data realizations? Data realizations is a more of a general term that would capture not just your climate scenario uncertainty. Let's say you have multiple emissions pathways like RCP 2.6, 4.5, 6.0, 8.5, like several different emissions pathways into the future, several different shared socioeconomic pathways. There are also other data inputs that you might be uncertain about that you can draw from a known statistical distribution. So let's say if you don't know a certain parameter of your species distribution model, it means that you can also integrate that into several discrete data realizations that we see here. And the problem of using conventional approaches to systematic conservation planning is that we typically ignore everything that is going next to this selected data realization. We assume that the data is looks like this. This is the distribution of the species that we're trying to protect. and we select or do the best, assuming that our data is correct. We prioritize, and then but when we try to evaluate this solution on the left to against all of the data realizations that we actually have, we end up with something like this. Actually, our conservation prioritization failed the targets repeatedly across several different possible data realizations. So this is a problem. Let's say if you optimize or you do your prioritization based on a historic species distribution model, based on where species used to be, and then you project into the future of where these species will end up, you are going to end up with something like this, because the species will decline under climate change, and then your protected area network is actually not that effective. What we want is something that looks like on the right. We want to integrate most, if not all, of the model data realizations that we have into a framework such that we can prioritize, such that we meet our targets on the bottom across most, if not all, of these data realizations. So even if we are ending up with something like this in the on the left, we've got two cells with features, and on the middle we've got three cells in the model, and as well as on the right we've got only one cell of the feature. We still end up protecting and meeting our targets across all of our data realizations. So this is what we would want. And the nice thing about the package that I'm going to tell you a little bit about is that it doesn't just allow you to do the fully robust solution. So on the first one, you see a not so robust or conventional approach to prioritization. There's absolutely a trade-off to be made here. In order to make this distribution shift more to the right, a lot of times it means that we need to select more conservation areas for prioritization. It does mean that we, by enforcing more constraints in our problem, we are reducing the total number of feasible solutions that are available in the model. And sometimes it also means that the solution is infeasible. If you are trying to minimize costs, you also find that your solution gets a little bit more expensive because you are selecting more parcels in the landscape by enforcing a fully robust solution. What we also do is allow for the relaxation of the fully robust solution such that we are transparent about the likelihood of us reaching a certain target. What it allows us to do is, if you see the green area under the curve, on the distribution of possible outcomes, and the red area here. The red area shows where we fell short of a particular target, and the green area shows that where we have met the target. The package will allow you to select or alter a so-called confidence level. So it allows you to ensure that this distribution, the area under this distribution, is at least as great as a certain level. It tells you what's the likelihood, what's the probability of you meeting a certain target. And you can alter this confidence level such that you can explore more feasible solutions. You're not just fully constraining yourself and sometimes ending up with highly infeasible solutions. So that's one of the other features that we have, software features we have implemented in the package. So that's what we mean by a partially robust solution. It allows you to be really transparent about the chance of you meeting your targets across your data realizations. Robust prioritizer is basically an R package that allows you to do the things I've just mentioned. It's based on mixed integer linear programming. So it means that in contrast to software like Marsan, which relies on simulated annealing, it uses the same approaches from mixed integer linear programming, which finds exact solutions. A lot of times you can find one single solution, but you can also reveal a portfolio of different solutions that has a certain guaranteed level of optimality. So how close you are to the true optimal solution if you are a nerd like me, which is trying to look at optimization algorithms, that's something that might resonate with you. But if you're the rest of the other people, it might not mean anything to you. But there are just basically papers that have shown that this approach would solve quicker than simulated annealing approaches. What it does is also it builds on the existing prioritizer framework, such that if you have your prioritizer code, if you have already done something with prioritizer, you can effectively use this and replace some of the objective functions that you use and add a couple of arguments, but still be able to use everything else that is built into the prioritizer package. It allows you to select the solvers, and you don't have to manually go into, let's say, your favorite numerical solver like Robi or Cplex in order to do your own thing. You can just prioritizer handles it all for you. So I also rely on some of these toolkits to such that your problems can rely on the same reusable framework and be solved efficiently. So what does it look like from a programmer's perspective in terms of implementing robust prioritizer? In a conventional prioritizer framework, you first start with defining your problem, then setting your objectives, you set your constraints, and then you set your solvers, and then you solve. So there are many different functions within the prioritizer package that will be reused, that you can reuse in a robust prioritizer framework. So effectively what it does is that you would need to swap in and specify a robust objective and a robust constraint, but everything else, let's say if you have locked in constraints for where existing protected areas are already in, then you can just use the same function call for prioritizer in robust prioritizer. You can set the same solvers, the sort of set of solution methods are roughly set the same, and you can also use things like other approaches in prioritizer to explore a portfolio of different solutions. So that's the beauty of integrating within the prioritizer framework. So I'll show you an example before I finish of systematic conservation planning in Victoria. So we came up with a simple example that to show you what this all looks like. So in the state of Victoria, we extracted feature data, so feature data of 18 different endangered species in Victoria. The initial data set from Paula McBoard and others is actually quite much larger, but we now just selected 18 different endangered species and looked at not just the current species occurrence, but also future its occurrence under future climate change as projected under the coupled model comparison project 6. So that's one data set that we use for future species projections. There's also the cost data that we brought in from the Human Footprint Index from Brooke Williams and others, as well as the locked-in constraints of current protected areas. We ensure that the cells that are currently within a protected area continue to be selected. So what is going to look like when we don't use a robust solver and just enforce for us to reach a 7% species representation target, assuming historical data. We find that actually, if we just set this target, we are not adding new protected areas. But if we evaluate that solution across time, if we evaluate what the current protected area network will do under future climate change, we find that the target, the relative target here, is breached across several different climate scenarios. So here we see that the higher emission scenario in purple and in blue, the RCP 7.0 and RCP 8.5, like we would see a drastic decline for the representation of the orange value parrot. And it means that we are, in fact, not doing a very good job under future climate change. we would therefore need a package like robust prioritizer to help us identify conservation or prioritization approaches that would lift us up from this such that it remains robust across the multiple different realizations of climate change that we have in our data set. What we then looked at is how we can exploit a partially robust. In this case, I assume that there's at least an 80% chance for us to reach a feature target, as well as a fully robust solution where we are ensuring that across all the time steps, across all the climate scenarios, we are reaching our target. And now we are indeed adding new protected areas, as we would expect, even to meet the 7% target. And here we are seeing some of the trade-offs between applying a robust approach versus not applying a robust approach. We can see here in the partially robust solution that we are lifting up the overall representation of the orange-bellied parrot, and of course there are other species that we have in the data set, that we ensure or we constrain it such that the representation meets the targets across counting all these time steps. It meets the target at least 80%, in this case 81%, which is doing okay. We are still seeing some breaches of the target for the higher emissions scenarios that we're looking at here in purple and in blue. If we adopt a fully robust solution, we are ensuring that the protected area meets the targets across all of these time steps, across all of the climate scenarios that we have in the data set. Of course, it still doesn't say anything after 2019, because that's where the data set ends. But now the probability, the likelihood of us reaching a target is up to 100%. And there are, of course, like some of the trade-offs here. We are increasing the total amount, the total cost of our protected areas 30% for the partially robust solution relative to the solution if we simply use the conventional approach, and 15% if we adopt the fully robust solution. So there are inherent trade-offs to be made in terms of like robustness. If we increase the level of robustness, how can we do it? We usually have to increase the amount of protected areas that we select, and therefore it will increase the cost, but at the same and reduce the total number of feasible solutions that we have. But I think it's pretty worthwhile for us to think very carefully about how and whether or not our protected areas will be sensitive under future climate change. So yeah, I'm happy to take questions, and like the nice thing is that like this package I've currently put online onto GitHub, so it's like fully open source, and I've also written like a lot of documentation together with Jeff to teach people how to use some of these additional functions. And so feel free to go online and read a little bit about how it all works. We have currently implemented only 2 objective functions that we would find in prioritizer, but ultimately what we want to do is we want to get feedback from a community of researchers, and I think CBCS is a great place for me to get feedback from different people in terms of like how you might see yourself using something like this, whether or not something like this will be useful, and what other new features or software features that you'd like us to put in place such that it will help you do your conservation prioritization more robustly. Thank you.
Thank you, Frankie. That's an amazing advance. I think that's really cool. I was just one question about your kind of conceptual framework, and I think you spelled that out so clearly. So maybe some of the nuance is lost because you're aiming for that to be really accessible. But it seems like you're assuming, the gap in that kind of conceptual framework that I'm wondering how we feel is that we're assuming that the future has some kind of inevitability about it, whereas actually what we only really know is where the species are now, and the future is very uncertain. We might models would tell us that this orange-bellied parrot's going to move to this place in the future, but we don't know that. And of course, models have varying levels of accuracy because of interspecies interactions or their habitat there. So with your robust future, how do you build in, like, we know where the species are now sometimes, but where they're going to be in the future has uncertainty built in. How do you balance that? When you're saying it's robust, how do we know that the species are going to be there in the future, or hedge our bets on that?
Thanks today. So the question is, I think there are a couple questions that I've trying to summarize here. So firstly, we're only modeling a certain discrete set of possible future outcomes, but the space of uncertain outcomes can be rather infinite, right? We are only modeling for future emission scenarios, but there are varying different other climate scenarios, varying different other sources of uncertainty here. And yeah, you're right that the level of robustness that you ultimately can achieve is dependent on like what sort of data you have modeled, and it only say that it's robust within your modeled futures. If you within the futures that you don't model, it's not able to say anything concrete about that. So let's say if we, in a couple of years' time, the IASA comes up with a new climate scenario, or if some new researcher comes up with a new species distribution model that tells us that the orange-bellied parrot is actually somewhere else, and that's like knowledge uncertainty, right? Or uncertainties, model uncertainty. So because we are uncertain about which model is correct and which model aren't, it doesn't really say anything about that. It really depends on your modeled uncertainty and how you would treat uncertainty, and it only says something about the uncertainty that you specify. It doesn't really say anything about the uncertainties that you don't specify.
Thanks, Frankie. That's really interesting. The relation yesterday was so you can find like suitable habitat for a species in say 2070. Does it account for the connectivity between current habitat and future habitat for a species that can't fly, so that they can actually move dispersed to the intervening time steps? Or is that just like loads of extra constraints and don't kill time?
Yeah. So the question is whether or not a framework like this will account for connectivity constraints and connectivity benefits for these different species. And the short answer is that it can account for some of these connectivity constraints through the existing functions that you already can access within Prioritizer. So within Prioritizer, you would have be able to specify, for example, connectivity constraints or additional rewards to your objective function to incentivize some sort of like agglomeration of these selected protected areas within a certain place, such that you benefit by the connectivity of your protected areas. And that's why I've decided to build this within the existing framework, such that you can use functions that are already built into Prioritizer to extend your work, so such that it's robust whilst it's connected. There's another layer to your question, as in like whether or not it accounts for connectivity over time. And the short answer is like currently no, because it doesn't say anything about the time connectedness of these different time steps that we have modeled. 2030 and 2090, the model currently treats it as the same as like the connectivity between 2030 and 2050. So it just doesn't say anything about the time connectivity, but the spatial connectivity can be specified as constraints or additional benefits to the objective, such that your prioritization would be more connected and represent some realistic sort of parameter values that you specify. Yes.
Yeah, really interesting. Just building on those two questions. So with that one, could you not just run it every 5 years? And if you have access to the species distribution models, then you just run it very frequently So you make sure that you meet your your targets through all those time periods, and if they were close enough together, then you're going to maintain reasonable connectivity. So you could do that, couldn't you?
Yeah, you can certainly run the model every 5 years and.
And so that gets to my question, which was how much slower than prioritizer is it when you're going to have these extra constraints?
Yeah, that's a great question, and well, it relates to the computational performance of the robust prioritizer. So it really depends on the amount of constraints, like the amount of model features you have. If you have like 16, 17, as in the example here, it runs fairly similarly, as in like 0.1 second and 0.01 second, you're not going to notice the difference. But if you have like more than 500 or 100 or 1,000 or something like that, then it can run significantly slower. Because the number of constraints increase exponentially as you layer in more and more different data realizations. So let's say if you have a model that not just looks at climate scenario uncertainty, but also looks at different model replicates, drawing parameters repeatedly and from multi-color simulation, then yes, you can significantly slow it down. And there are an increasing amount of approaches from the operator research literature that would help us do something about that. So right here, we only assume these data realizations to be discretely distributed, and it will increase over time. The solve times will increase with respect to the amount of scenarios that the data realizations that you put in. There are robust optimization approaches such as can set uncertainty sets, like for example polyhedral or ellipsoidal uncertainty sets that can specify that space of uncertainty to be a sort of polyhedron or a ellipsoid. That would help really reduce the total number of constraints, and that would help with the solve times. We've not yet implemented that here, but that's something that we've been actively looking at as in this version.
Yeah, thank you for this, really an exceptional talk. I really enjoyed it. I have so many questions, and most of them are really nerdy, so I'll spare everyone those. But I think it's sort of relating to everything that's sort of already echoed about all the different things you could incorporate into this, given we're pretty much uncertain about almost everything. I was wondering, in your plots though, you had this run for different climate change scenarios.
Yep.
But the scenarios could also be the source, could be part of the uncertainty set. I mean, it would explode because you multiply all of your uncertainties by each scenario. Have you tried to run that and see what the answer is, or would it just be ridiculously slow in it?
Well, it's not that. Well, in the online documentation, I've ran an example that based on a data generating process that would not just look at like climate uncertainty, as in like we are uncertain about how many degrees we are going to warm in the next 100 years, but also the model replicates within the same model. Let's say in your same representative concentration pathway, you have parameter uncertainty. You fit a species distribution model, and that comes with a parameter that is you are uncertain about, such that different models can be right. So yes, we've run that, and welcome to check out the approach. But yes, we've done that, and yeah, it would quite quickly increase the amount of constraints, and sometimes it would make a lot of solutions that would otherwise be feasible infeasible. So that's something to be wary of. It's like, okay, what's the limit? And of course, that people would like go down rabbit holes of trying to model many different layers of uncertainty, and because like once you have model uncertainty, then you have like different models that could be right, and then you start to weight these. So that I would also advise like people trying to do this to not try to go down a rabbit hole, because ultimately this is trying to generate some useful insights for policymakers, for decision makers to make a decision in time.
True, but we wouldn't want to give undue confidence for the future, so we tell policymakers it's definitely going to be there in the future, but we don't know that it's going to be in the future. I think we just might need to temper that advice because of, as Matt said, there's so many things you're uncertain about.
Yeah, that's right. Yes.
Thank you so much for the presentation. Actually, I'm interested in the optimizing method you employ. Actually, the optimization with constraint is a really, tricky part. So I'm just wondering what kind of algorithm approach you employ for your research. And there are several approaches, like maybe Gaussian methods, linear programming methods, and there are several approaches. So what kind of methods?
Yeah, so the question is what sort of optimization approach that we use.
Yeah.
And I try to not be too nerdy about that. So we use the mixed integer linear programming approach that is already employed within the prioritizer package.
Is it
And
linear?
so it's linear programming.
Linear programming.
Linear programming.
So why do you use the linear programming, not use the non-linear programming or Bayesian programming? Or Bayesian? So why do you
First, well, certainly we can, but currently with a lot of the systematic conservation planning problems here, we are dealing with many discrete decision variables. So, like flipping back here, like we either put a protected area in that place or we don't put it there. So this is like an example of binary decision that we get. It's either 0 or 1. So if you are using a continuous optimization algorithm such as Bayesian optimization, then you probably not be able to model something like this. And the second reason is that we are frequently dealing with a large number of decision variables. We're not just dealing with 1 or 2 decision variables. We're trying to figure out whether or not we want to put a conservation area here or here or here. So it really depends on the total number of planning units you have, and like the continuous optimization approaches don't really scale with the total number of decision variables. Okay. Is there any questions on?
There's thanks and compliments online, but no questions so far.
Thank you for the talk. That's very interesting and clear. I have this silly question. So for this example that the solution is more protected areas is needed, is it there possible that the result actually tells it's not more protected areas needed, but shifted protected areas needed, such as the species may not stay for this protected area in the next 10 years. So we might need to focus on the shifted area to put all the resources and management in the other places. Is that possible for the results?
Thanks. The question is whether or not we should be thinking about shifting protected areas instead of static protected areas, right? And that's not a silly question at all. That's in fact like the research thread of many researchers. I've wrote a paper on like how we can increasingly add protected areas over time in the case of conserving koalas in New South Wales flexibly. So. And of course, there are other papers that have been written about moving protected areas and also like pop-up conservation approaches where we put in a conservation area for a certain given period of time. Let's say the birds come in a particular week and then we put in a conservation area there. Or there are certainly a lot of approaches that would do that. So right now, I'm not sure, but I don't think prioritizer would do time series or multi-stage optimization approaches that can feasibly be a next step, or you can do what Anne said and run the optimization for every couple of years and figure out what to do next. And that's probably also the decision horizon that a lot of these decision makers have. So short answer, that's definitely feasible, but that's not implemented in the package.
Thank you.
Yes.
This might reflect my little understanding of this narratives, but So when you discretize your, say, parameter space to do scenarios, is it possible that you may come up with some scenarios that are not feasible? And is there a way to discount those? in your optimization?
Yeah, thanks. The question is whether or not there are instances where when we generate scenarios, we would end up with an infeasible solution. And the answer is definitely yes. Even in this example, we in some climate scenarios for some particular species, not the orange belly parrot, we would find the total amount of representation for certain species to be too small for us to even reach the target. Even if we selected the entire state for protection, we will not meet our targets because so once we, let's say, do a high emission scenario for the species in 2090, it would fall beneath the target even if we selected everything for protection. So yes, definitely that will happen, and that also echoes Matt's question about whether or not we want to increase the total number of replicates or models. So yes, there's definitely a problem here. So that's why there's the partially robust approach that would allow you to ensure that the constraints can be met up to a certain confidence level. So that means that like for some of these realizations, we can allow the solution like the targets to be breached because there's no other way. Let's say in a high emission scenario, the total number of species for a particular total number of species in a state falls beneath the target. So even if we did everything we can, we are not going to find a feasible solution, and that's why we can sort of like discount or relax the constraint in a rather transparent way.
Alright. Good, Frankie. Yeah, thanks, Frankie. Yeah.